How can a capacitor give back more voltage than it receives? That is the strange behavior observed in negative capacitance, especially in certain nano-oxide structures, where under alternating current, AC conditions, the system appears to amplify voltage instead of storing it. In classical electronics, capacitance is always positive. You apply a voltage, and the capacitor stores energy in an electric field. But in some ferroelectric nanomaterials, particularly oxides like doped hafnium oxide, scientists have observed negative differential capacitance, where a small increase in voltage actually causes a decrease in stored charge, suggesting energy is being released rather than absorbed. This paradox challenges our traditional understanding of electrostatics and energy conservation at the nanoscale. So what causes this counterintuitive effect? The answer lies in ferroelectric phase transitions. When a material switches between different polarization states, it can temporarily occupy a metastable configuration that lowers its energy by releasing charge. In nanoscale oxides, this switching happens rapidly and non-linearly under AC conditions, resulting in an apparent negative slope in the charge-voltage curve. Example, in ferroelectric field effect transistors, FEFs, negative capacitance is exploited to reduce the voltage needed to switch states, boosting energy efficiency in next-generation logic devices. Analogy: it is like pushing a swing just as it's already coming toward you. Your small push adds up with the swing's own momentum, creating an unexpectedly large effect. The negative capacitance paradox offers not just a scientific curiosity, but a potential revolution in low-power nanoelectronics, where quantum-scale behaviors are harnessed for real-world performance. Why do certain ferroelectric or high-K nano-oxide layers, when driven by an alternating voltage, exhibit an effective negative capacitance, temporarily amplifying voltage rather than storing charge, defying the everyday rule that capacitance is always positive? In classical dielectrics, capacitance reflects the system's ability to store charge linearly with applied voltage, yet at nanoscales, thin ferroelectric films and interfaces can transiently reverse this behavior under AC, suggesting an internal energy release that momentarily boosts the external signal. So far, so good, until we examine what underlies this counterintuitive response. The negative capacitance phenomenon emerges when the intrinsic energy landscape of a ferroelectric material, in which polarization states sit in a double-well potential, couples to a series dielectric or semiconductor layer. Under a small fast AC perturbation, the ferroelectric's polarization can traverse its unstable region between wells, releasing stored energy and effectively reducing the net voltage drop across the system. This dynamic can manifest as an apparent negative differential capacitance in impedance measurements. At its core, two intertwined mechanisms drive the effect: polarization dynamics. In a ferroelectric, flipping polarization from one well to another involves passing through a high-energy state. When an AC field nudges the system toward this unstable saddle point, the ferroelectric briefly supplies energy back to the circuit as it relaxes. Okay. Series stabilization, pairing the ferroelectric with a conventional dielectric or semiconductor, stabilizes the overall system's energy, preventing runaway switching. The series element absorbs the excess polarization, converting the ferroelectric's unstable region into a useful negative capacitance window. Yet even this mechanistic view conceals finer scale intricacies. The observed negative capacitance depends sensitively on frequency, temperature, film thickness, and interface quality. Too slow an AC drive allows full domain switching, restoring positive capacitance, while too fast a drive fails to trigger sufficient polarization dynamics. Atomistic defects, domain wall pinning, and strain gradients in ultra-thin films can truncate or distort the negative capacitance window, making reproducible observation a delicate art. At even finer scales, non-equilibrium and quantum effects emerge. Nanoscale ferroelectrics can host flexoelectric contributions, polarization induced by strain gradients, that modify the energy landscape. Quantum tunneling of domain walls or localized charge trapping at interfaces can further skew the timing and magnitude of the energy release. These mesoscopic phenomena mean that the effective negative capacitance is not a simple material constant, but a dynamic, context-dependent response. In essence, negative capacitance in nanostructures reminds us that at the frontier of materials physics, familiar notions, like always positive, capacitance can invert when energy landscapes, interfaces, and nanoscale dynamics conspire. Harnessing this effect promises ultra-low power transistors and novel energy conversion devices, but only if we master the multi-scale interplay of ferroelectric switching, dielectric coupling, and interface engineering. Negative capacitance, NC, refers to the counterintuitive regime where increasing the voltage across a device causes its stored charge to decrease. In specially engineered nanometer-thick ferroelectric oxides, the collective flipping of electric dipoles can drive the system through a transient state in which its capacitance becomes negative. When placed in series with a conventional dielectric capacitor, this effect can amplify voltage internally, enabling gain in a passive circuit. NC challenges the classical expectation that capacitors always store more charge when voltage rises. Ultra-thin hafnium oxide films within a transistor gate stack have demonstrated a temporary negative capacitance region during polarization switching, boosting the gate voltage. It is like stepping on a spring, and instead of compressing normally, the spring suddenly pushes you up higher than your step, briefly giving extra force. In a normal capacitor, stored charge and applied voltage are directly proportional, so pushing the voltage up always increases the charge. Negative differential capacitance means that over a certain voltage range, pushing the voltage further actually makes the charge drop. This only appears under specific biasing and dynamic conditions in ferroelectrics and does not persist as a steady-state behavior. Understanding NC requires rethinking how we design circuits to harness this transient reverse response. During a voltage sweep on a ferroelectric layer, the measured charge voltage curve bends backward in places where the capacitance is temporarily negative. It is like turning a car's steering wheel slightly in one direction and finding that the wheels briefly turn the opposite way before correcting. Ferroelectric materials have two stable polarization states separated by an energy barrier. When the polarization flips from one orientation to the other, it must pass through an unstable region where small changes in the electric field lead to opposite changes in polarization, hence negative differential capacitance. This transient NC arises during the fast domain wall motion that reconfigures the material's dipole alignment. The phenomenon is rooted in the kinetics of dipole nucleation and growth at the nanoscale. Time-resolved measurements on barium titanate films show rapid domain boundary movement correlating with negative slope segments in their charge response. It is like a ball rolling over the crest of a hill where, at the very top, a slight push forward makes it roll backward before it descends the other side. The free energy profile of a ferroelectric features two minima corresponding to its polarization states and a hilltop between them. Around that hilltop, the energy curvature is negative, meaning the system resists small displacements in the expected direction. In electrical terms, this negative curvature translates into negative capacitance, since capacitance is linked to how the system's energy changes with charge. Stabilizing that hilltop region through proper circuit design reveals the NC effect in a series stack of a ferroelectric and a dielectric. The dielectric's positive capacitance balances the ferroelectric's negative region, allowing a stable amplified voltage state. It is like balancing a marble on the very top of a dome. Small nudges make it roll backward first before it finally tips off. Negative capacitance appears prominently only when ferroelectric layers are scaled down to a few nanometers, where their internal electric fields and surface effects dominate. Interfaces with adjacent materials, metals or high-K dielectrics, provide charge screening that helps stabilize the otherwise unstable polarization state. Confining the ferroelectric in ultra-thin films sharpens its energy barrier, enhancing the negative curvature region. Thus, the magic of NC relies critically on nanoscale dimensions and precise interface engineering. 5 nanometer thick films of doped hafnium oxide grown on silicon have shown room temperature NC when paired with a matching dielectric. It is like tuning a musical instrument's reeds so finely that they resonate only within a very narrow thickness range, producing a rare overtone. Under alternating current or pulsed voltage, ferroelectric polarization cannot follow the drive instantly, leading to phase-lagged and nonlinear responses. Within certain frequency bands, where the driving period matches the domain switching kinetics, the ferroelectric exhibits a negative effective capacitance. Outside that window, it behaves like an ordinary capacitor or a hysteric material. This frequency-dependent NC highlights its transient non-equilibrium character. Impedance measurements reveal a negative imaginary capacitance peak at kilohertz frequencies, aligned with the material's intrinsic switching time. It is like pushing a child on a swing at just the right rhythm to make it briefly swing backward before going forward again. Harnessing negative capacitance in the gate stack of field effect transistors can reduce the required voltage swing to switch the device, lowering power consumption. By amplifying the internal gate voltage, NCFETs can achieve sub-threshold slopes well below 60 millivolts per decade, breaking the classical thermal limit. This promises highly efficient electronics for mobile, Internet of Things, and neuromorphic computing. NC thus offers a pathway to sustainable scaling beyond conventional CMOS limits. Prototype FETs with hafnium oxide-based ferroelectric gates have demonstrated steep switching at sub-0.4 volts, far lower than standard designs. It is like unlocking a door with a whisper instead of a shout, drastically reducing the effort needed to open it. Measuring negative capacitance requires carefully separating true NC signals from parasitic resistances, inductances, and leakage currents that can mimic the effect. Ensuring long-term stability in ultra-thin ferroelectrics without dielectric breakdown or fatigue under repeated cycling is also difficult. Integrating these materials into existing semiconductor process flows demands compatibility with high-temperature anneals and chemical stability. Overcoming these hurdles is crucial for bringing NC-based devices to market. Early demonstrations of NC transistors suffered from drift and endurance issues, prompting the search for new ferroelectric compositions and electrode materials. It is like fitting a delicate crystal ornament into a high-volume assembly line without it cracking under repeated thermal stress. Advances in atomic layer deposition and two-dimensional ferroelectric crystals are paving the way for ever-thinner, more uniform NC layers compatible with advanced technology nodes. Machine learning-driven materials discovery is accelerating the identification of low-loss ferroelectrics with rapid switching dynamics. Beyond low-power electronics, negative capacitance concepts may inspire novel sensors, energy harvesting devices, and active metamaterials. Mastering NC and nanostructures could thus unlock transformative applications across electronics, photonics, and beyond. Research teams are exploring NC effects and layered perovskite oxides as potential elements in next-generation radio frequency circuits. It is like discovering a hidden spring in mechanical linkages that, when tapped, releases stored energy to amplify motion without any motor.